I just read an article that blew my mind, literally blew my mind. And what I think is going to happen, it is going to change the entire crypto currency, technology. Blockchain is dead.
There's been a lot of talk about Hashgraph, and this is a little more, this would be a little more coy, saying Hashgraph is here to destroy blockchain.
Swirls is labeling its Hashgraph technology as a radically different approach to distributed consensus. They're also claiming that this new approach will be able to solve scaling and security issues.
Of proof of work, such as long transaction times, and you don't need miners, and it avoids miner concentration and that incredible amount of power needed to process a block.
So, since Monday night and the Mike Maloney video, I have been absolutely just obsessed with learning as much as I possibly can about Hashgraph.
So we've been looking at this amazing new technology for about a week now, and what I find so incredibly amazing is that it holds the promise to solve all of the problems that the other distributed network ledger systems have. Bitcoin, once it started to scale up, it turned out that it used an immense amount of energy to run the system. And also, as it scaled up, it became slower and slower and slower to where it was no longer a currency. It was basically a speculative vehicle. People could make some gains in purchasing power on it. But it wasn't something that you could stand in line at a Starbucks and pay for a cup of coffee for. A friend of mine just did a transaction that took 4 hours for confirmation. And so this is incredibly fast, pretty much instantaneous. The number of transactions that it can process per second is mind-boggling compared to Bitcoin, and it uses almost no power. So it solves all of the issues that I had with Bitcoin.
So what happened? You could say Bitcoin came along and said, you know what? We could do money without any government. We could do something better than the fiat government, the fiat monies that are out there. Revolutionary concept. We'll do it by making people do proof of work. So you buy a supercomputer, you feed lots of electricity to it, and then you too can help be part of the system and make it fair. And it's so hard to do that we can trust that no one person can dominate it. And so therefore we're all going to be fair and trustworthy, and we will ensure that the ordering of our transactions are agreed on by all of us. It may not be terribly fast or fair, but we'll agree on them, and then nobody can forge money. No single government, no single person would be able to forge money in our system, counterfeit money. Kind of revolutionary. And there's a lot of applications for that. And even at 3 transactions per second, you can see that there's an enormous market with Bitcoin. I mean, it really is a big deal. So I'm just going to tell you in about 2 minutes how it works. Here's the whole algorithm in 2 minutes. And if you don't like math, you only have to suffer for 2 minutes. We want speed, right? So here's the idea. Alice has that red envelope. She has created a transaction. She wants everybody to know it. So she tells someone totally randomly. This is about the simplest algorithm I can imagine. And now Dave knows it too. 2 people know it. And then each of them tells someone randomly. Now 4 people know it. And then each of them tells someone that they pick at random. Now 8 people know it. It explodes outwards, exponentially fast, and soon everybody knows it. And if you attack one of these computers and shut it down, it doesn't matter. It'll still just spread out to everybody else that it wasn't being attacked. There's no one computer that's a bottleneck. And there's no one computer that has to call everybody up one after another and tell them. Alice doesn't have to call each person and tell them individually. She just tells someone and then tells someone else, and then they're telling someone else, and it just explodes.
Is it random out of the pool of people that don't know yet? Yeah.
Ha! Almost. Actually, what you do is you call somebody, but then you make sure you only tell them things they don't know. And so what will usually happen is you're going to have a whole bunch of information. When you call a random person, some of it they'll know, some of it they won't. And there's really clever ways to make sure you don't tell them something they already know. That's a really good question.
Well, I have a dumb question.
That's good too.
What if you attack the only person that knows, in this case Alice? Then no one will know.
If an attacker shuts down your computer, you are not going to be able to bid in our stock market. You are not going to be able to play our game.
So how is that fair?
Well, that's not a failure in the consensus algorithm. That's life. That's the truth. But what doesn't happen is the whole network shuts down. And with something like the leader-based systems, the whole network shuts down if they attack just the right person and keep following the leader. So let's be clear here. Nothing is 100% secure. If you have a third of the people being evil, they can do terrible things and corrupt the network. If you have a botnet that can shut down a third of the network, they can freeze the whole network. If there is an earthquake that chops off a third of our people, then the whole network freezes. Nothing can help you with these things. But nothing less than a third is going to hurt you. And that's the point. I want to add a tiny little bit of information to each of these messages, like 1% bigger, just a few more bytes to each message. That's all I'm going to add, is a little tiny bit of information to each message, and that's going to be enough for you to see an incredible history of how we've all talked to each other, which is weird. And then we're going to get consensus for free. You will not have to talk to anyone, and you'll have perfect consensus with math guarantees that you're right. That's weird. That's crazy. So let's talk about this. We all have these messages, and you know, I just showed this animation of everyone talking to each other. Let's draw a diagram of it. No one ever draws diagrams of this. I want to draw a diagram of it. So here's a network with just 3 people, Alice, Bob, and Carol. Time goes uphill. You see the 3 circles at the bottom are Alice, Bob, and Carol. Those are just the 3 at the bottom. Each of these circles then, above that, represents an event of somebody gossiping to someone else. So look at the top circle in the whole thing. That's the last event that I have in this diagram, and it is in the Bob column. And it has a line going down to a circle in the Carol column. That top circle represents the event where Carol called Bob and told him everything she knows. All the messages she knows she gave to Bob. This diagram is a way of seeing the whole history. If you look at this diagram, you can see how we talk to each other and in what order we talk to each other. And in fact, if you told me there was some information in Alice's circle at the very bottom there, I could just follow the lines and see how the information flowed through the network. It's really kind of cool. And if you told me there was something in Carol's circle at the bottom, I could see how it flowed. And for any given person, I could tell you which of the 2 messages they got first. You can just watch how everything flows through the network from this diagram. It's a really cool diagram. Nobody ever draws these diagrams. But this is a diagram you could draw that would show you the whole history of gossip. Now, we can gossip about transactions. We could gossip about identities. We could gossip about information that we find interesting. But what if we were to gossip about gossip? What if we were to be gossiping what we know about this very picture? What if we were to do gossip about gossip? In other words, when I call you, I give you everything I know. What I mean is I give you all the pieces of this very picture that I know. That's weird, very recursive, self-referential. We are going to gossip about the picture where the picture is the record of how we gossiped. Bizarre. But we're going to do that. So each of these circles now is actually going to be a little data structure in our memory that is the message that we're sending people. Now we do want to have some transactions, so you'll put the transactions inside the circles. But in addition to a circle having to have the transaction, it will also remember 2 lines going down from itself. The thick line for what column it's in and the thin line for who was talking to that person. Just 2 lines, 2 pointers, 2 hashes. We're building a graph held together with hashes. In math, this is called a graph. It's held together with hashes, so we call it a hash graph. So the hash graph is the history of how we've all talked to each other. But all I have to do is send you the transactions I was going to be sending you anyway, digitally signing them, sending you timestamps, all the stuff I would have been doing anyway, plus 2 hashes. That's it. Each message just has to be bigger by 2 hashes. And in fact, for various reasons, I can compress each of those hashes down to 1 or 2 bytes, and I'm fine. I still have total security. So we started with gossip. That's the fastest way to get your transactions out. We added a tiny bit of overhead And for free, we got the whole hash graph that shows the entire history of how we've all talked to each other. And now we know what each other knows. I know what you know. And I know what you know about what she knows. And not only that, I know when you learned about what you know about what she knows about when he learned this thing from him. I know it all. So the short answer is a blockchain is a chain of blocks and a hash graph is a graph held together with hashes. Here's the less short answer. In a blockchain, and when you say blockchain, I'm gathering that you mean proof of work. You're not talking about one leader-based systems. You're talking about proof of work. In a proof of work system, the way it works is that you have a chain of blocks, each of which has the hash of the previous one, so nobody can go back and change something in the history. It makes it immutable. And then, to put the next block on, somebody will come along and put the next block on. That's great. The problem is if two people put the same next block on, then we as a community have to chop off one of them and only accept the other one. And we do that by voting with our feet. We decide which of the two to expand. You always try to extend the one that's longer. And then eventually it's so much longer that we just throw away this one and no one ever bothers with it. That's how it works. The problem with that is that if we were forking this way too often, we would get new forks before we finish chopping off the old fork. And the whole system would collapse. We'd keep sprouting new forks all the time. So we have to slow it down. So how do we slow it down? We do proof of work. In a proof of work system, the whole purpose of the proof of work is to make it run slower. That's interesting. I don't have a part of my engine in my car whose purpose is to make my car run slower. But that's the whole point of proof of work, is to make sure that we're only adding a new block every 10 minutes, or some of the newer ones would be much faster, but to make sure it's slow enough that the community as a whole will have time to figure out which of the chains is longer and always go with the longer fork. To do that, you have to solve a math problem. The math problem does involve taking a hash and trying to find one that will have certain zeros and so on. But it doesn't even matter what you do for your math problem. The point is, it's a useless math problem, but it's really hard to solve, so you need a supercomputer and lots of electricity. Problem. Anytime that you need a supercomputer and lots of electricity and there's economies of scale, you're going to have minor consolidation. Fewer and fewer people are going to have that supercomputer. And if it uses lots of electricity, everybody's going to move to where the electricity is cheap. And you can have geographic consolidation. And once you've got minor consolidation and geographic consolidation, then our beautiful trust model maybe is not quite as trustworthy. If we all live in one spot and the government of that spot nationalizes all our mining rigs and makes them start extending the shorter branches, then they've destroyed the entire system. So that's how the blockchain works. For us, you don't have a chain. You just have that picture I showed with all the circles with lines. And anybody who wants to add a new circle does it. In fact, typically in the experiments I run, each individual computer is adding 10 new circles every second. So it's like a miner in Bitcoin mining 10 blocks a second. Every single miner mining 10 new blocks a second. In blockchain, that wouldn't work because it'd be too fast. We wouldn't be able to chop off these forks. But in Hashgraph, we like forks. Nothing ever gets chopped off, so there's no problem.
So is it the overlay of this voting algorithm that kind of
Yes.
validates that there's not different kind of information?
That's it. In fact, that goes back to the question you had asked earlier, too. In a blockchain, it's easy to put them in order. It's just the order of the chain. But in this system, maybe it isn't so obvious. Oh, there's the graph. That graph there, it isn't obvious what order to put the circles in. But because the graph represents the history of how we talked, I know enough to run in my head one of those old voting algorithms, and I can put every single circle in order. And so in my head, I do actually put every single circle in order. That puts all of my transactions in an exact order that I know everybody agrees on. And then if you double spin, I know which of the two stores got it first and which one got it second, and we say the money actually went to the first store and not the second. So all the problems go away. So we get beautiful advantages by having a graph rather than a chain, but then you say, well, how do you get consensus? And we do that by doing the virtual voting. But you can only do the virtual voting because I have this history of what we all know and how we talk to each other. And the reason I have the history is because I did gossip about gossip. I did a hash graph. And that is how this is different from other systems that use a graph. There's a bunch of systems out there that draw pictures that look like that picture. But their picture doesn't represent a history of how we talked to each other. So they couldn't do virtual voting. So they couldn't get all the advantages of that. Also, people talk about 51%. Although we've also had people say it correctly. Bitcoin is a 34%, a 1/3 vulnerability. Turns out there's a math theorem. Everybody's 1/3 vulnerable. There is no 51% vulnerable system out there. They're all 1/3 vulnerable. So some of the things I was worried about was, well, if we have a bunch of nodes, each of those computers is a computer. It's a full node. It's a miner. And what happens if we have geographic consolidation and maybe a country builds a firewall around them? What happens if they turn off the firewall? Could we get a different chain on the inside versus the outside? I don't know. Maybe we could. Oh, we'll build a partition detector. Okay, what if they start flickering the firewall? Will that interact badly with our partition detector? I don't know. Or what if they start just delaying things? Delaying packets enough so maybe we start to have a difference of opinion on which chain is longest. Or maybe they do other malicious things. I started worrying about all those things. For example, what if those yellow nodes are compromised? A third of our computers are bad, or in this case, a third of our hashing power is bad. And we have a firewall, and the firewall is colluding with the 1/3. You could imagine on any given yes-no question, like, we have a fork of these two chains. Should I extend this one? Is this the longer one? Any yes-no question. You could imagine that the honest nodes outside the firewall happen to vote yes. The honest nodes inside the firewall happen to vote no. And the dishonest nodes are duplicitous and vote no to the guys inside and yes to the ones outside. And they're actually going through the firewall because they're colluding. And now we have a real fork. The people inside think that 2/3 of us are saying no, and the people outside think that 2/3 of us are saying yes. This is a problem that destroys it. You end up with a false consensus with only 1/3 of us being compromised. Now, that attack doesn't really bother me because every system has that attack. And I'm only putting it up here because it was one of the things I was thinking about. We have a decades-old theorem that says every system is vulnerable to 1/3. The proof of that theorem is basically that picture. That's the proof of the theorem. That's a math proof. But it's interesting to know. We just need to be clear as a community on what our security is, and none of us are more secure than 1/3 of the influence. So if you use hashing, it's 1/3 of the hashing power. If you count IP addresses, it's 1/3 of the computers. If you do proof of stake, it's 1/3 of the coins, or 1/3 of the stake. But nothing can survive 1/3 being compromised, and this is why, assuming the bad guys have the ability to do things like firewalls. So I'm just telling you some of the things I was thinking about. We as a community, are talking about these things, which is good. Well, actually, mathematically, it's 34. To some degree, the two numbers are so close, it doesn't matter a whole lot. But you're also saying, in practice, would there ever be such a firewall? Guess what? There happens to be a cryptocurrency that is concentrated in a country that happens to have a firewall.
Right.
Okay.
Well,
Okay. So is that a problem or not? And honestly, I pretty much trust the government of that country to not shut it down. But the whole point of Bitcoin was to not have to trust anybody. So the fact that we have to now trust a single party is kind of annoying.
So we're doing permission networks, but we do have demo apps, and one of them is a cryptocurrency. So you could say we have a little cryptocurrency there. Here's the deal. If you have a community that can reach an agreement on the exact ordering of the transactions, and you know when you've reached agreement, then you and everybody independently is processing these to update the state. So you can imagine a state that remembers how much money is in every wallet. And a transaction moves money between two wallets. But if the transaction is supposed to move money from Alice to Bob, but Alice doesn't have any money in her wallet, then the transaction doesn't do anything. So what you do is you have everybody agree on the order of these transactions. Maybe Alice actually tries to send money to two different stores, but she only has enough money in her wallet for one of those two transactions. What do? We all come to an agreement on the ordering of the transactions. We all know that she gave it to Bob first and then Carol. So we all then, on our own, move the money from Alice to Bob because there was enough money when that transaction happened in the official order. But then the next one in the official order was moving from Alice to Carol. There wasn't enough money at that point, and so we all ignore that one and don't let it move any money. So we're all in agreement to make sure that there's no double spending or no creating money out of thin air because you transfer money from an empty wallet to another wallet and the money actually gets there. We're all enforcing the rules. And the math proof says that if you have a consensus algorithm that's not going to be broken, that you're going to end up with this proof of consensus, and as long as less than a third of us are trying to destroy the system, the bad guys will fail. And so just almost for free, you get, if you've written the rules that we're all enforcing to ensure that, say, the money supply is fixed, then you get the money supply being fixed. No one person or no small group of people can forge money. No small group of people can double spend. No small group of people can convince a store that you've paid it when you really haven't paid it. All of that happens for free if we can put transactions in order and have Byzantine guarantees.
This changes the entire economic model. You can imagine users who don't have to pay for a server because there is no server, it's just their computer while they're playing. Right now, some kid has to pay Microsoft $10 a month to play Minecraft, and they can only have 11 kids playing at a time. But this could be free, and you could have 1 million kids playing at a time. So it's a different economic model. How about an indie game developer that would love to do an MMO but can't afford the big servers? They don't have to.
But for that, he would need access to a public version.
No. So an MMO can actually be just the players themselves running it. It doesn't have to be public. Probably what you would actually do for an MMO, as I think about it, is that you would have part of it being public and part of it being a whole bunch of little privates, and they would all be connecting to it. It'd be almost like side chains. But it depends on how you want to do it. But if you wanted to, you could actually start with purely private if you wanted to.
Yeah, so sure, good question. So right now we're doing permission networks, and our customers really don't mind it being patented. In fact, some of our customers in the financial industry actually like the fact that we do it this way. So it just hasn't been an issue. It's literally a non-issue. We are also talking to possibilities of, for example, you have some of the big stacks like Hyperledger that allow you, that are pluggable, and there's a consensus module at the bottom. And we would just say, hey, anybody who wants to set up a permissioned ledger can use this for free. But if you would like greater throughput and greater security and fairness, then you can just buy the premium module from us and plug it in at the bottom of the stack. So, we're talking about doing things like that in the future. So again, it's not a problem. People are used to that sort of thing. It's like databases. You can get open source databases right now, and a lot of people use those, but then some people pay for the premium model that isn't open source. So, both coexist. There's room for both. And for public ledgers, we haven't even done anything with that yet, but, we'll worry about that when we get to it.